Hello and welcome to our lesson on Pythagoras' theorem. In this lesson, we'll build on your existing knowledge of right-angled triangles by diving into Pythagoras' theorem. We will begin by introducing the theorem. This powerful tool allows us to relate the lengths of the sides in a right-angled triangle. We will then apply this theorem to a practice problem. In our previous lessons, we've focused on understanding right-angled triangles. You now know how to identify a right-angled triangle by looking for the 90-degree angle, as well as the components of a right-angled triangle, including the hypotenuse, the longest side opposite the right angle. With this foundation, we are ready to introduce Pythagoras' theorem. Before we learn about this famous theorem, let's quickly understand some of its history. Although Pythagoras is given the credit for this theorem, he was not actually the first to discover this relationship between right-angled triangles and the hypotenuse. He was just the first that we know of to write a proof for it. Some of the earliest ideas of the theorem can be found in Egyptian hieroglyphics. Pythagoras' theorem is a fundamental result in geometry, particularly in dealing with right-angled triangles. The theorem states that a squared plus b squared equals c squared, where c is the hypotenuse, which is the longest side opposite the right angle, and a and b are the other two sides of the triangle. This theorem helps us find the length of any side of a right-angled triangle when the lengths of the other two sides are known. Let's have a look at a visual proof of Pythagoras' theorem. Suppose we create a square with a side length of a plus b. Inside this square, we place four identical right-angled triangles with base b and height a. Notice that by placing these four triangles, an inner square is formed with side length c. The area of the large square is a plus b squared. The area can also be seen as the sum of the area of the inner square and the area of the four triangles. The area of the inner square is c squared. Each triangle has an area of half AB, so the combined area of the triangles is 2AB. This means that the whole area of the square can be written as c squared plus 2AB. We can therefore write that a plus b squared equals c squared plus 2AB. Now we can simplify this equation. Taking the left-hand side of the equation, we can expand the brackets as follows. If you're unsure about how to expand brackets like this, take a look at the lessons from the algebra module. We can then set this equal to the right-hand side of the equation to get the following equation. We can then subtract 2ab from both sides of the equation. This leaves us with a squared plus b squared equals c squared. And that's Pythagoras' theorem. Remember, this theorem only applies when we're dealing with right-angled triangles. Let's apply this theorem to a problem. In this right-angled triangle, the lengths of the two shorter sides are 3 centimeters and 4 centimeters. What is the length of the hypotenuse? Pause the video to try and solve this yourself. First, recall Pythagoras' theorem. A squared plus b squared equals c squared, where c is the hypotenuse and a and b are the other two sides. Let's substitute the known values into the equation. So we can write 3 squared plus 4 squared equals c squared. We then calculate the squares to find 9 plus 16 equals c squared. Adding these values, we get 25 equals c squared. To finish our calculation, we take the square root of 25, which gives c equals 5. So the hypotenuse is 5 centimeters. In today's lesson, we delved into the foundational aspects of right-angled triangles, focusing on Pythagoras' theorem. We explored Pythagoras' theorem, which states that in any right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. This theorem was visually demonstrated by considering a square of side length a plus b and considering the areas of four identical triangles within the square. We then applied this theorem to solve an example problem, finding the length of the hypotenuse when the other two sides were known.